Now let's derive the relation between the instantaneous position of a point as a function of time and the instantaneous velocity of the point at the same time. Given a graph of x versus time, or x of t, we can calculate the instantaneous velocity of a point at any time. Recall that the average velocity, which we denote as v bar subscript t1 to t2, is given by x at time t1 plus delta t, minus x at time t1, or delta x, over delta t. The average velocity is the value of the velocity between 2 points in time. The instantaneous velocity, on the other hand, is the value of the velocity at only one point in time. You could say at a given instance, in time. Hence the name instantaneous. The instantaneous velocity at time t1, v of t1, is defined as the average velocity in the limit, as delta t tends to 0. So in other words, the instantaneous velocity v of t1 is equal to the limit, as delta t tends to 0, of the average velocity. Substituting the above equation for v bar, we get that v of t1 is equal to the limit, as delta t goes to 0, of x of t1 plus delta t, minus x of t1, divided by delta t, or the limit, as delta t goes to 0, of delta x over delta t. Recall that this is the definition of the first derivative of x with respect to the variable t, which we denote as d by dt of x of t1. We can write this in short, as x dot of t1, where the single dot above the x indicates a single derivative with respect to time. Looking at the graph, we can explain the instantaneous velocity as follows. To find the instantaneous velocity at time t1, we just keep making delta t smaller and smaller. As delta t approaches 0, delta x also becomes smaller and approaches 0. And the instantaneous velocity at time t1, which is the ratio of delta x over delta t, becomes more accurate. From the previous slide, we derived the equation for the instantaneous velocity. We found that the instantaneous velocity at time t1, or v of t1, is equal to d by dt of x of t1, which is equal to x dot of t1. Since t1 can be any value of t, we can rewrite this equation as v of t is equal to d by dt of x of t, i.e., the first derivative of x of t with respect to time t. The yellow line shown here is the tangent to the curve at time t. The value of v of t is equal to the slope of this tangent line. The slope can be calculated directly from the graph by finding 2 points on the yellow line. The first point shown here has coordinates t1, x1. The second point has coordinates t2, x2. The slope then is equal to x2 minus x1, or delta x, divided by t2 minus t1, or delta t. Note that you can choose any 2 points on the line, and the value of the slope will always be the same, regardless of which points you choose. Now you can interactively use the sliders shown here to change the values of t1 and t2, and see the effect on the instantaneous velocity at time t1, and the average velocity between times t1 and t2. As before, use the mouse to drag the slider bars, or use the right and left arrow keys on the keyboard, after clicking on a slider to activate it. Note that as t2 approaches t1, the value of the average velocity approaches the value of the instantaneous velocity. When you'd like to continue with the lecture, please press the play button. A bus stops at a routine bus stop. It then travels along a straight road, so that its distance from the bus stop is given by the equation x of t is equal to 2 times t raised to the power 2 minus 0.150 times t raised to the power 3. Calculate the average velocity of the bus for the time interval t equals 0 to t equals 8 seconds. Calculate the instantaneous velocity of the bus at time t equal to 6 seconds. How long after starting from rest is the bus again at rest? In this example, the displacement equation for the bus is given as x of t equals 2 times t raised to the power 2 minus 0.150 times t raised to the power 3. We need to find the average velocity of the bus at time interval t equals 0 to t equals 8 seconds. We know that the average velocity, v average, is the ratio of displacement to time interval. In other words, it is the ratio of delta x to delta t. If subscript 1 denotes the initial position, and subscript 2 denotes the final position, then v average is equal to x at time t2 minus x at time t1 over t2 minus t1. Now let's substitute the values of time t into the displacement equation. First, at t equal to 0, we substitute the value of t equal to 0 into the displacement equation. And we get x of t equal to 0 meters. Similarly, at t equals 8, we substitute the value of t into the displacement equation and get x of t equal to 51.2 meters. Next, to find the average velocity at time interval t equals 0 to t equals 8 seconds, we use the average velocity equation and substitute t equals 0 for t1 and t equals 8 for t2. This gives v average is equal to x at time 8, which is 51.2, minus x at time 0, which is 0, divided by 8 seconds, minus 0 seconds, which gives v average equal to 6.4 meters per second. The instantaneous velocity of the bus is found by taking the first derivative of the displacement equation with respect to time. That is, Vx is equal to dx over dt. We are given the displacement equation as x of t is equal to 2 times t squared minus 0.150 times t cubed. So taking the first derivative of the displacement equation with respect to time gives us 4 times t minus 0.45 times t squared at time t equal to 6 seconds. The instantaneous velocity of the bus, Vx, is found by substituting t equals 6 into the equation above, and we get 7.8 meters per second. In solution part B, we found the instantaneous velocity to be 4 times t minus 0.45 t squared. To find the time, when the bus is again at rest, we set the instantaneous velocity of the bus to 0. We thus end up with the equation, 4 times t, minus 0.45 times t squared, is equal to 0. Which can be rewritten as t times 4 minus 0.45 t, is equal to 0. This means that either t equals 0, or 4 minus 0.45 t, is equal to 0. T equals 0 is an answer, but the question specifies that the bus starts at rest, and to find the time when it is at rest again. So t equals 0 is not the answer we are looking for. The correct answer is therefore the solution to 4 minus 0.45 t equals 0. Solving this equation, we get t is equal to 4 over 0.45. Thus, the value of t is found to be equal to 8.89 seconds. In the next 3 slides we will generalize the equations that we derived. For the average position, the average velocity, and the instantaneous velocity. In terms of the instantaneous position x of t, we will generalize those equations to another quantity, say q of t, by simply replacing x of t with q of t. We can do that because there was nothing in the derivations that restricted the use of those equations for just the position coordinate x of t of a point. The formula we derived for the average position in a time interval, in terms of the instantaneous position, is as shown here. The average position, x bar from t1 to t2, is equal to the integral of x of t, dt, from t1 to t2, over t2 minus t1, which is equal to the area under the x of t curve, from t1 to t2, over t2 minus t1. In the derivation of this formula, there was nothing that restricted the use of the formula for just the position coordinate x of a point. In fact, x of t can be any other quantity that is defined as a function of time. So in general, if we have a time graph of a certain quantity, say q of t, and we want to find the average value of the quantity in a time interval t1 to t2, we can simply replace x of t by q of t in that formula. So we now have q bar from t1 to t2 is equal to the integral of q of t, dt, from t1 to t2, over t2 minus t1, which is equal to the area under the q of t curve, from t1 to t2, over t2 minus t1. The formula we derived for the average velocity in a time interval, in terms of the instantaneous position, is shown here. V bar from t1 to t2 is equal to x of t2 minus x of t1, over t2 minus t1, or x of t1 plus delta t minus x of t1, over delta t, where delta t is t2 minus t1. We note that the average velocity in a time interval can also be called the average rate of change of x, or x dot bar in the time interval. Thus, we can generalize this formula by saying that x can be any other quantity q. Then the average rate of change of q, or q dot bar in a time interval, is given by q of t2 minus q of t1, over t2 minus t1, which is equal to q of t1 plus delta t, minus q of t1, over delta t. The formula we derived for the instantaneous velocity, in terms of the instantaneous position, is as shown. V of t is equal to dx of t, dt. The instantaneous velocity is also called the instantaneous rate of change of x of t with time, or x dot of t. Thus, we can generalize this formula by saying that x can be any other quantity q. Then the instantaneous rate of change of q of t with time, or q dot of t, is given by dq of t, dt.